two of our colleagues won't be here today, so I want to make sure to get all of these important announcements on the recording. A week from today, we won't meet in this classroom. I'm going to be at a conference out of the country, and I'd hoped to find someone to administer the exam to you, but I was unsuccessful. So what that means is that you're going to do a take-home exam. The exam will be open book, open note, and you'll have a period of 6 hours during which you can access the exam. The exam is going to be available on MU Online, so at 4 p.m. a week from today, exactly 1 week from today, magically it will appear on MU Online. You'll see Exam 1. And so you can access it there, you can download it, print it out. And then you'll have, my hope is to write the exam so that students can finish it in between 1.5 and 2 hours. But even though I think that everyone should be able to finish it in 2 hours, you still have until 10 p.m. to finish the exam and upload it to MU Online. And so it's the same kind of electronic submission that we're doing for the homework assignments. Now, although it's open note and open book, I require that you complete the exam by yourself without any collaboration from other students. And so that means that you should be in a completely separate physical location from somebody else who's taking the exam. Different building. So that's just how we're going to do exam number 1. Are there any questions or concerns related to that? It's going to be a PDF that will just magically appear, and then once you print it out and solve your answers on the paper, then you scan it and upload it to an area that's going to be available. Does that answer your question?
Yeah.
I kind of cut you off there, sorry.
You cut me off.
Okay. Yeah.
Will you specify, I don't know if this type of question will be on there, but will you specify if it can be done in Excel or if not?
Good question.
And how we'll upload those?
Yeah, I'll specify. And if you have supporting files that are something besides besides like handwritten calculations, then you can attach more than a single file for a submission. You could submit, I think, an infinite number of files, but hopefully it won't. It'll be less than infinity, I hope. Other questions about the exam? If you look at the course schedule, next week was supposed to be a short period of lecture followed by the exam. And so since that's not possible, I've included the lecture component. We're going to talk a little bit more about hydrographs next week. I've included that in tonight's lecture. And so I think we're going to probably use the full class period tonight. All right, so if anything else comes up, questions about the exam, please let me know. The next homework assignment related to hydrographs, technically you could finish it before the exam, and if I had thought about it earlier, before I made the course schedule, I would have made it due on the day of the exam, but since the original due date, according to the course schedule, was going to be March 8th, I'm just going to leave it at that. So you've got 2 weeks to finish the homework assignment. And as per usual, that'll be submitted on MU Online before class begins.
Will this homework be covered on the exam?
Yeah, it will. So the material that, that we're going to be covering in class today, the concepts particularly are things that you should be acquainted with for the exam. Now the problem solving, I'd have mixed feelings asking you to do calculations that you maybe hadn't even completed the assignment on. So it may be something very simple, like a simplistic question, but certainly not to the depth that the assignment itself is. And when we get to the unit hydrograph, for example, tonight, when we talk about unit hydrographs, I'll give you a sense of what I think a fair exam question might be related to that.
This is the last question. But I mean, obviously, homework is 1 to 7, lectures up until today. You know, the exam, but do you have book sections?
Yeah, I think, I couldn't tell you offhand, but I think on the course schedule, it identifies which book sections go along with the exam. And since you've got open access to the book, I'm not going to ask as many concept questions as I ordinarily would. I'm going to leave those for our final exam because I don't think that there would really be any point of me asking you to define things, define certain concepts, and then you just look it up out of the book. That doesn't really show any sort of understanding. So the exam will more be focused on problem solving and maybe describing processes, but it won't be like vocabulary definitions, because you'll recall I've given you a handout of some concepts that I'd like you to memorize by the end of the semester. Well, it won't be to the end of the semester until I assess that. It won't be on this test. Any other questions? Mm-hmm. Say that again?
Last class, you said whether it's a grad class.
Yeah.
There's a lot of material that we haven't covered in class.
So what I mean by that is that there are more detailed explanations of concepts than we have time to go over during our weekly class meetings. And so it's not like there's some completely new concept that we haven't discussed at all. It's really more of the depth of explanation about, for example, precipitation and what causes it. We spent an hour talking about lifting and the transition between moist air and precipitation, but there's a lot more than that verbal description I gave you that's found in the book. And so what I think you should be doing in the textbook isn't necessarily hunting for things that we didn't talk about, but looking for another point of view on the things that we have discussed. And I mean, there are lots of ideas in there that we didn't cover and we won't. And I think it's important for you to just to skim over the rest of it. I mean, it all depends on what you want to get out of the course, whether it's being prepared for an exam or whether it's a comprehensive understanding of hydrology. And I mean, those aren't mutually exclusive, but the point is there's a lot of material that we just can't cover in like a 15-week semester. And so I hope you're skimming through the book each week. In Chapter 8, we may only get 5 of 10 pages or something, but those other 5 pages are worth looking at. All right. Well, today we're going to be talking about basins, losses, excesses, and hydrographs. And that is a long list. I'm going to switch from heat to cool, I think. A little stuffy. This is a conceptual model here. This equation is something that I had to wrestle with a couple of years ago when I was doing a project for the West Virginia Department of Environmental Protection. And the DEP is charged by the legislature of doing a statewide water balance. And so the legislature thinks that and they're right, one of West Virginia's resources is that we have a lot of water. And there are plenty of states in the U.S. that don't have the same abundance of water resources. And so the legislature wants to try and look at places in the state where there's an excess supply of water and a reliable source that could be used for agriculture or industry. And so they asked the DEP to start thinking about ways to quantify that. So take watersheds, big watersheds, and analyze those watersheds to find out how much excess water could be utilized for commercial gain. And so where I was involved on that project was trying to estimate the evaporation in a watershed out by Greenbrier. And it's pretty tricky, as you've already got a taste of. And believe me, the actual full-scale sophisticated evapotranspiration models that are used in research are lots more complicated than we did on the homework assignment. They take into account actual measurements of a lot of things that we just kind of assumed, like the emission energy from the Earth, how much energy it's being radiated. So it's really tricky to measure ET, which is evapotranspiration. But what this model says is that if you think about mass balance relationship, if you think about a so-called black box and keep track of what goes in and what goes out of a volume, a control volume, you can think of the watershed as that control volume. And what this equation is saying is that we have water coming into a watershed and water coming out of a watershed. And let's look at how we can do sort of an accounting of all of it. We'll start with this Q in. Some watersheds have a river that's flowing into them from a watershed upstream. Many don't. We're going to look at some pictures today that introduce the concept of stream ordering, but some watersheds are downstream of other ones, and so you'd have actual water coming in through rivers. Now, PR is the precipitation. That's the moisture from above that can fall onto a watershed, and that's also considered as an inflow. All these other terms have a minus sign here, indicating that it's flow out of the box, besides the actual stream discharge. Now, it's the stream discharge that most of the time commercial enterprises want to kind of harness. You know, if you think about the water company, here in Huntington, it's West Virginia American Water. And they have a facility right on the Ohio River where they're drawing the water out of the river, purifying it a little bit, and sending it into the water network. So Q out is going to be kind of like what we could harvest. It's the leftover water. After, there's a lot of evaporation, so that's ET. GR, groundwater recharge, is that the water is, of course, infiltrating into the soil. And we talked a lot about the factors that influence that infiltration in the past. Delta S is surface storage recharge. And you're hearing a lot about that right now in California, how because of all the precipitation they've been having, the reservoirs are full, they're being replenished after years and years of reduced levels. And so the delta S is just the fact that if you have any kind of a reservoir, then the levels can go up and reduce the amount of flow that's available for discharge. LQ would be if inside of a watershed there is someone using it for agriculture, industry, mining, that sort of thing. And so large quantity users, and AG, I guess, you can lump the LQ and AG together, agricultural water consumption. So the Q out is just what leaves that fraction of the water that leaves a watershed compared to what came in.
Yeah, why does the GR and delta S have a positive negative sign?
That's a good question. In the case of the groundwater recharge, it's because at different times you may actually have groundwater contributing to stream flow. So let's say that it's been very dry for several weeks. You still might have flow coming out of a watershed even though there's been no precipitation and even though there's been no inflow from other streams. So you wonder, if it's been dry for so long, why is there still water in the rivers? And it's because the water that's underground can sometimes come back up from underground. So think about a hillside, and then here is a river, and we've got water down here into the river. If it rains, then the water infiltrates into the soil, but then it can make its way, the base flow, and contribute to the actual water levels. And so during dry periods, then the groundwater recharge may be contributing to the outflow. But if it's raining, then it might be that the water levels, that the infiltration is occurring, and so we're actually recharging the groundwater rather than discharging the groundwater. And the same thing is true of delta S. You know, and the reservoir water levels can be rising or falling. And so that's just the same kind of idea that inside of this control volume, the water can be trapped or detained temporarily. Okay. Before we can find, therefore, if we are interested in the flow coming out of a watershed, or the word catchment is sometimes used to mean like a smaller watershed. catchment is sometimes used to describe urban areas or urban watersheds. So in a catchment, one of the things that's going to influence how much outflow there is are abstractions. And this term is most widely defined as just the difference between precipitation and rainfall excess. And this is an important distinction to make. And sometimes precipitation and rainfall excess are used interchangeably. So there's a subtle distinction between the two. If you think about the water that falls from the sky, not all of that water is going to contribute to runoff. And in fact, even if you account for infiltration, not all of the precipitation minus infiltration is going to be runoff, because sometimes the water gets stuck in other places. And two of the places that are pictured here is like surface puddles that would be on a really flat sidewalk, or even if it's not puddling, the moisture can be wetting a surface. And so that water is retained or temporarily detained and then evaporates because of the contact with the surface there. So abstraction is just either the amount of water or the timing delay that occurs when rainfall starts compared to how much actually contributes to the discharge. We'll talk about a couple of processes that contribute to abstraction. So it can slow down the peak flows. So if we think about trying to prevent the effects of urbanization, then abstraction is a good thing because it's delaying the onset of peak flow. It's also reducing the quantities. So we want to try and quantify abstraction because the size of a culvert or the depth of flow in a channel, those are all going to be affected by the amount of abstraction. And also, the kind of surfaces that the water comes in contact with is going to change the quality of the water as well. If it's carrying sediment downstream, or if there happens to be oil or grease or salts or grit, whatever the water is coming into contact with, its quality is going to be affected through that contact as well. So interception is one of the types of abstraction. We're not talking about football interception. What we're talking about is when the raindrop is falling through the sky, sometimes it's coming in contact with plants. So like trees or buildings or even crops like is pictured here. So it's just the interception component of abstractions is how vegetation is temporarily or permanently delaying water from reaching the surface. You can see a raindrop here. It's stuck on a plant. If it continues raining, it might tip that water over and all of it would dump onto the surface. Or it's possible that the water could evaporate and actually not make it to the bottom. So what do you think are some of the factors that affects how much water is intercepted by plants? Excuse me? The amount of plants. Okay, that's a good factor. And what do you mean? Mm-hmm. You're right. And so what's your rationale there? Like why do you think that's the case? Okay. Yeah. And so you're thinking in terms of like the surface area of a plant. And so remember last week we were talking about clays and how clays have a really high surface area. Was that last week or 2 weeks ago? Okay. Plants can have a high specific surface area just like other things can too. And so the type of vegetation has an effect. Here is a table that shows what percentage of precipitation is going to be intercepted by different species of plants. I realize that this is probably a bit hard for you to see in the notes, but I'll mention that I upload the PDFs of the notes to MU Online if you ever need to zoom in for a clearer view of something for the homework or for any other reason. So one thing you'll notice is that different types of trees have different percentage interceptions, and then the seasons also play a role. So why do you think that a let's see, a deciduous hardwood that during the winter is only intercepting 6%, but in the summer may be intercepting 21%. And what's the effect? Absolutely, yeah. And so if you stand under a tree trying to avoid the rain during the summer, you'll probably be more successful than during the winter, depending on the length of the storm and so on. Now, some of these things are quite low here, like oak litter. Only 2% interception, oak litter. And that could be, we're talking now about twigs and branches that have fallen directly onto the ground. And then the other point about it is the closer it is to the ground, the less likely it is to have interception, because it may be splashed by raindrops that are actually bouncing up from the ground. If it rains really hard, you can see splashing coming up from the ground. And sometimes when you're measuring rainfall, there are guidelines on how high above the ground surface the gauge is supposed to be to avoid that backsplash. So how much rainfall is intercepted may depend on the storm. How intense a storm is could completely overwhelm and saturate a plant. Like these percentages, if it's just a really low, if it's a tiny storm, maybe it would intercept 100% of the rainfall. There may be times when it just rains for a few minutes and not a single drop of water gets through a really thick tree canopy, like these trees out here on 3rd Avenue. Those trees could be 150 years old. They're enormous. But then there could be storms with a lot of sideways wind, and where the humidity is higher and just that the interception is much lower. Density of vegetation, the age, health of the vegetation. So those are some important factors. There's actually an empirical method that's been developed to try and quantify the effect of interception and estimate how much of the precipitation is left over after interception has sort of played a role. And the interesting thing about this empirical method is it has two parts. One is just related to how much water a tree can store. That's S. And then the term that's in the brackets here, this is just kind of like a logarithmic function that says what percentage of that storage is actually going to be available as you compare the amount of precipitation to the storage capacity of the plant. And remember how we were talking about sometimes in a really, really heavy rainstorm, the interception capacity of a tree may be completely overwhelmed? Well, what's inside the brackets here accounts for that. And so in a small storm, 100% of the storage may be available. But in a larger storm, a smaller fraction of the storage may be available in the end. So that's what this first term is. It's just looking at the raw storage capacity of a plant. And there are tables similar to the one that's shown here on the right that characterize for different species of trees how much storage you might see. Now the second term here is related to evaporation. And this is a little bit counterintuitive that you'd think during a rainstorm there's going to be evaporation. But it actually happens. And remember that during a rainstorm, the high humidity sometimes is only aloft. It may not be down below that the air is fully saturated with moisture. So we know that rainfall occurs when there's lifting of moist, warm air. Well, if the clouds are above and there's collisions of those droplets that coalesce into heavy enough particles that fall downward, the point is that there can be appreciable evaporation while it's raining. And so if we go back to the picture of that raindrop, this water could evaporate, a fraction of it anyway. And that's what the second term of this empirical equation says, is there's a leaf area index, K, that's usually given in a problem statement, that tells you kind of, if you look down on a plant from above, how many layers of vegetation there are on average as you're going downward. And that's the way I think about it, it's a reflection of how thick the canopy is. And so that E, which is the evaporation depth per hour, is multiplied by T, which is the storm duration, And then combining those two things together, that gives you an idea of how much interception there is. And so I'd like you to get a feel for how to use this equation. Let's try and predict how much rainfall is left over after there is interception. And so here's the formula for interception. I give you some parameters in the problem statement there. Calculate I, but then calculating I isn't the end of the example, because you need to think about of the storm that originally occurred minus the interception, that leftover amount is what actually is going to make it to the ground and either will run off or will be intercepted. Okay, so the interception has two components, the amount that is stored on the tree and then the amount that evaporates from the tree. And the reason why those two are additive is that whatever evaporates from the tree opens up as additional storage on the tree surface itself. And so if there had been no evaporation, then once the leaf area was completely saturated with water, then that would have been the end of the interception. So in the end, though, I'm not asking you just to calculate the interception depth, which is about 9.9 millimeters, but rather you have to find out what's the rainfall excess. In this case, the rainfall excess that we're talking about is how much water, the difference between what's coming from the sky and what's making it to the ground surface. And so the amount that's available for runoff and infiltration is just going to be the difference between the precipitation depth that was the original starting point and the interception. So it's 28.1 millimeters is the leftover. Now, how accurate is this? Man, probably just barely accurate enough to even put into a textbook, because there's so many variables. If you think about, there are things like temperature isn't directly in that formula. So how do you suppose how accurate you're going to be able to estimate the amount of evaporation during a storm? And the leaf area index, that could vary from tree to tree. Like if I characterize the leaf area index for these big gigantic trees here that are hundreds of feet tall, it may be a completely different leaf area index for an oak tree, but is not quite that tall. So you always have to take approaches like this with a grain of salt. They may be important in illustrating a phenomenon that you have to be aware of, but it's really only just a starting point, or maybe like a holding place until you find a more accurate way of estimating something.
So this is just to look at summertime, I guess, and the leaves all around the trees.
Yeah, because let's see, in this case, I guess it wouldn't necessarily matter because we were doing spruce, right? Spruce tree. And some of the things like a hardwood that's leafed and a hardwood that's bare has different. But here I think spruce is an evergreen tree that would have the same leaf area index and same storage regardless of season. Now, probably the evaporation would have been different during the winter compared to the summer, but we don't have any information on the example here that we have to distinguish between the season. I think on the homework, though, problem 1, I tell you that you should use a leafed hardwood tree rather than a bare hardwood tree. So you will have to distinguish between the two on the assignment. Okay, so the water can be intercepted by vegetation, or it could be intercepted by buildings. You know, sometimes during a rainstorm, if the rain is coming and there's wind driving it, you could maybe just stand on the dry side of a building, and then that's going to reduce the amount of water that gets to the ground. Sometimes depression storage is a pretty important factor, an abstraction, just puddles. You know, here's a picture of some water that isn't going to necessarily contribute to any surface flow. It eventually will evaporate, or it will eventually infiltrate, but over the short term, it's just whatever water is here is not considered excess, because it's not going to be contributing to the outflow from a catchment. It can be depressions in the ground. Storage can also be surfaces that need to be wet. And here is a picture at the Shannon Airport in Ireland of a wet runway. And there have been characterizations of different types of surfaces and how much depression storage you can expect from them. So a flat pavement may hold on to between 1.5 and 3.5 millimeters of water. And so what it means is that you could have that amount of precipitation and there would be no surface flow at all. It would wet the surface but nothing more. And so different types of pavement probably have different types of depression storage as well. You know, like an asphalt that is a little bit more porous, and you can kind of see the voids at the surface would probably have a higher depression storage than a smooth concrete, because there's just going to be less specific surface area in the case of a smooth concrete. And of course, we've talked about the effect of slope before, and why I think you can already kind of understand that a steep pavement is less likely to have a high amount of depression storage, just because at the angle the water is going to start moving at it's not going to be quite as deep before it can start moving. There's an attraction between the surface and the water, but the steeper it is, the more likely gravity is to overcome that attraction. All right, so all the way down to forest litter. And in the case of forest litter, you have a lot of depression storage there, just because there's so much that needs to get wet. All the leaves that have fallen to the ground, and they're starting to break down, but there's just layer after layer of leaves that can become wet before there's any surface flow over forest litter. So slope is included in that table in an indirect way. Specific surface area is as well. In the case of forest litter, there'd be a very high specific surface area compared to a flat pavement. The affinity of water to the material, and we've talked about the attraction that water has with things like silicon, you know, glass, and also if it's been wet in the past, it may be that the depression storage is less than this, because maybe it rained yesterday and the forest litter isn't completely dried out yet. And so that's another example of the antecedent moisture condition, and that's something that affected infiltration rates as well. If it was already wet, then there's going to be less of a capacity the next time a storm event rolls around.
What if forest litter have a high depression storage, but a low interception?
Well, it depends on when like how you draw the line between interception and depression storage. Interception usually is meant for things that are above the ground. And so forest litter that, like big branches that are maybe not laying on the surface itself, but the forest litter where it's like branches that are broken or decaying leaves, I think, is going to be lumped more towards depression storage than towards the, let's see, where was that? The forest litter, was it on this table that we were looking at it before? Yeah, hardwood litter, oak litter, and so on. Yeah. I think because it's not preventing it from getting to the ground. it's still, you know, if those little twigs are laying on the ground, they're not preventing the water from getting to the ground, but what the depression storage is it may get to the ground, but it's not moving anywhere. So it's preventing overland flow. Does that make sense? Yeah. At the very least, rapid infiltration. You know, like we had the assumption of continuous ponding, and so water that is bound in the forest litter may eventually percolate down to the ground, and it may eventually infiltrate, but it's interfering with the continuous ponding that would have to be there for maximum infiltration. But you know, some of it will evaporate off of the forest litter, some of it will just stay there. I mean, I don't want to draw like these artificial distinctions and say like if the water gets to the forest litter, it's never, like that the 7.6 millimeters is just going to stay there forever, because some of it may eventually drip down. But in the case of all these abstractions, it's either a reduction in the quantity or a delay in the timing. And it can have the same effect regardless of whether it's lost forever or if it's just delayed, because we're wondering what does it do to the peak, and it's going to delay the peak regardless of whether it's releasing the water for overland flow later or never at all. Okay, so Q is what you're developing in hydrology. We want to know what flow rate is going to be coming out of a watershed in response to a storm. And we're interested for a lot of reasons, because it can affect the quality of the water, the amount of the water, this is a picture of an inlet structure that's used for drinking water. I had a similar thing. This picture isn't taken from Indiana, but when I was working on my PhD, I had some equipment set up at a drinking water plant in Carmel, Indiana, which is north of Indianapolis. And they had a really, really big flood that changed the turbidity of the water, and all of the fertilizer that had been laid down early in the spring and pesticides suddenly were washed into the river, and they had to basically shut down drawing from the river, although it wasn't because there wasn't enough water, it was because the water quality was very poor in the spring, and so they had to switch to a backup auxiliary well that they had. So it can, you know, the flow rates can affect both the quality and the amount of water for drinking purposes, and then also it can have a big effect on flooding, as we've talked about a lot already. Okay, you've already been introduced to the word hydrograph, which is a visual representation of precipitation. And so these two figures are showing the relationship between a hydrograph and a hydrograph. It's input and output. And if we have a conceptual model that looks at rainfall information and then predicts how much flow is going to be in a river, we need to basically link the input and the output. And that's what programs like HEC1 and HEC-HMS, later in the semester, we're going to start using software programs that do that. You've already done it with StormCAD. You know, with StormCAD, you could define a rain event, and then it would assume the peak flow rate. And, you know, it would size the pipes, it would analyze the pipes based on the size that you told it, assuming the maximum flow rate in the rational method. This is actual data, though, that was showing it got rainy, and then there was runoff. And what this curve looks like is partly affected by the rainfall, like where it is, how intense, if it's all at once or if it's a steady, even flow over time. Looking at the sinuosity of the streams is a factor. If you look at these streams, it looks like they're mostly straight, and so that the flow is going to drain into this river very quickly compared to if it was a lower slope inside of the watershed, and if the streams were meandering. And here in West Virginia, hydrologists talk about many of the watersheds being flashy, meaning that as soon as it rains, you have a very quick response in the stream. And the reason for the flashiness of watersheds in West Virginia is because we have very, very steep topography, and that the water is able to move over the surface pretty quick. This is kind of just a diagram of lateral streams, these inflows from very small ephemeral creeks that are only flowing when it actually rains, going into a river that's getting gradually, the shape of this just means that the more contributing streams you have, the more flow there's going to be, and then the channel is itself wider. So this is kind of just a conceptual diagram that's showing why the streams get bigger as you go downstream. And then there may be a certain spot that we call the outlet that we're interested in. But as we've talked about, an outlet is just a point of view. We may have a culvert crossing this stream, and so we could call this our outlet. And all this other stuff is still happening, but as soon as we say that this is our outlet, then that makes our watershed only the area upstream of that that's contributing to the flow at the outlet that we're interested in. Here are some different types of drainage basins, and this is largely a function of geology in an area. There are places in the eastern panhandle of West Virginia, for example, that have trellis type streams. Like if you look at aerial maps, you'll notice that it seems that the streams are kind of straight there. They don't meander in the same way like this is more if you were looking at an aerial photo of Huntington. The streams kind of just are all over the place in a pattern that's called dendritic. But in coastal areas, like the coastal plain that's in the eastern panhandle of the state, then you may have streams that are a lot more regular in their direction. And then there are combinations of these two extremes, rectangular and trellis, where it's the soil's resistance to erosion that kind of affects where the streams go. And the streams go where the soil erodes the most quickly. That's the definition of the stream, is it's the low point in the topography that just whatever scour moved sediment downstream, it made it so that the water would go there even more next time because the ground level is lower and there's a greater energy differential between where the water falls and where it's going to. Stream ordering is kind of an interesting idea because it can give you an idea of why certain locations are more prone to flooding. And it's kind of an obvious, straightforward thing that the more upstream tributaries there are, the bigger the peak flows are likely to be. But a first order stream, here represented with the number 1, is someplace that during a wet weather event there isn't going to be any upstream contributions to it. It's only receiving overland flow in a first order stream. So it would just basically be sheet flow to the first order stream. And you'd have to go to a pretty small watershed size to see a first order stream. We're talking maybe less than an acre. But then a second order stream is where you have the combination of 2 first order streams. And you'll notice that when you get a third order stream is where you have more than 2 second order streams coming together. And what would then make a fourth order stream is where you have 2 third order streams coming together. So the classification system is just kind of, in some ways, not really meaningful from an analytical or quantitative standpoint. You're not going to look at a stream and know from the ordering what the flow rate's going to be. But it can sometimes tell you about the water quality that you could expect, because a first order stream only is going to be having flow when it's actually wet weather. Then the water that you see there is probably going to not have any effects of base flow, so it's not going to be groundwater that's coming back up from the surface. In addition to these ordering classifications, there are also just some terminology here, the perennial, intermittent, and ephemeral. And I've got a couple of pictures to illustrate the difference between those. In the case of a perennial stream, it's where water is present all of the time. This is a picture from the Wasatch Mountains in Utah, and this is a really famous trout fishing stream called the Provo River. And you'll notice that there is snow on the mountains here. And that's what makes this a perennial stream, is that all through the summer there's snow melting in the mountains, and that's what feeds that Provo River. We have perennial streams here in West Virginia, and they're not fed by summertime snow melt. They're fed by groundwater flowing towards the stream, and so that there's always water present. In contrast to that, an intermittent stream is one that only has water flowing through it during a wet season. And so during the wet season there will be water there continuously, even when it's not raining. But usually an intermittent stream is much larger in scale than an ephemeral stream. So you'll notice here the picture of the ephemeral stream, this is just kind of a ditch. And this is a low point where water will flow to it when it's raining, but the ephemeral stream won't have continuous flow at any point during the year. It would need to have rained within maybe a day to see any kind of moisture inside of the ephemeral stream. This is a figure that illustrates the same watershed during two different times. And during the dry period, the thick black line shows the stream where you can actually see water in a channel. And the shaded areas are showing seepage, which is the water coming up out of the ground, like the ground itself is wet because the aquifer levels are high enough there that it's contributing to the flow. And so during dry weather, the reason why there's still a flowing stream here is because there's groundwater seepage in these shaded areas. But in the case of during and after rainfall, you'll notice that the stream reaches much farther up into the watershed. And I see this with my own eyes in my backyard when it rains, that when it's actually raining, it's like my whole backyard is full of lots of little streams. But when it's not raining, then there's just a tiny trickle through only like the main low point in the holler that I live in. And so this figure kind of illustrates that, where you draw the stream doesn't just depend on the low points in the watershed, but it also depends on your threshold. Like how much upstream contributing area do you have to see before there is a flowing stream. And as it's raining, you may see that dendritic network extend much further into the watershed. Okay. What's this called, this kind of figure? Hydrograph, that's right. And so this is the rainfall graph, and below it is the hydrograph, which is runoff. Now, this hydrograph is taken from just a small part of the watershed. And here's Illinois, so we're talking about the central part of the United States. Within Illinois is a watershed that we're going to zoom out onto this watershed, but so far this hydrograph is from a small part of the watershed. That's why only this small area is circled in red, is to illustrate that this is very flashy. You see how as soon as it rains there's an instant response. So these peaks are very responsive. Like this pulse of rainfall is directly related to this peak. And then there's another pulse of rainfall. And then this peak. And then it looks like the watershed is draining. So this is a very flashy, responsive watershed with a small drainage area. In this case, 0.2 square miles. So if we zoom out a bit, and we now have a drainage area of 3.2 square miles, why do you suppose that it's less flashy? Like physically speaking, any guesses on why these peaks are kind of smearing together in the way that they are? Think about there's rain over the entire area in red. Why do you think the peaks are blending together? Okay, so the base flow, we're talking about like the groundwater that's contributing to the stream? Okay, what was your idea?
It takes longer for a walk across this area for this area than this normal area.
Travel time.
Okay.
Yeah, that's an important part of it too. So think about if I take a big 55-gallon drum and I pour it in a pipe all at once. If I go 5 feet away from that pipe, it's going to flow all at once. But if I go 200 feet down the line, some of it's going to trickle, then there will be a big flow, and then it will taper off. So the further away you get, the peak is spreading out in both directions. The flow is diffusing. And so there's a spatial averaging. It's sometimes called routing or delay. That the bigger the watershed area, it's partly because there is going to be base flow, and partly it's just the travel time. The water that's, if we're talking about the same area of interest, the same outlet right here, the water that rained in the faraway part is going to take a long time to finally get down there to the outlet. And so this pulse right here, the travel time was short when it was the 0.2 square miles, and so the peak happened very quickly. But that pulse of rainfall right there, some of it will get to the outlet quickly, but some of it will take a long time to get the outlet. And so the peaks start to smear. That's what we see is the larger in scale we get, as we look at now 16.6 square miles, the peaks have completely smeared together. And then if we zoom out even further to the entire watershed, 43 square miles, then the peak is smoothed even more. So if you look at, this effect is visible any place you look. I was looking at stream gauge data for the Sacramento River a couple of years ago, and the Sacramento River drains an entire, like almost all of Northern California. It's huge. But like when they say they've had rainy weather, you see the river levels going up very slowly, and then they go down again very slowly. Compared to a stream here in West Virginia that, number one, it's steeper, but also it wouldn't have such a big contributing area, then the response would be much more rapid. This is an important trend here, very important. So this is an example of it's material we're covering today that the concepts could be included on the exam. And so I'd hope that you'd be able to describe in your own words why we see these individual peaks in a smaller watershed but don't see it in a large watershed.
It's kind of a conception that I haven't explained. Is there a term, like a single term that represents this phenomenon?
Routing. Yeah. If you want me to boil it down to a single term, like if I'm doing like a Trump briefing and I want to like distill it down into the essence, they say that they're trying to get his national security briefings down to like a single word, like bomb, so he can. That's a joke I saw. But anyways, routing is the word that I use to describe this effect. All right. Two different kinds of overland flow. The Hortonian overland flow is at the surface. That's caused by saturation from above. And then there's saturation overland flow that is, it rains and it raises the water table, but then the water table migrates gradually towards the stream. So in this case, in the Hortonian overland flow, the wetting front is at the surface saturated, and it's moving sideways towards the stream. Saturation overland flow is a lot slower than Hortonian overland flow. And in fact, it's probably a misnomer to even be calling it overland flow because it's through the subsurface. It's not over the land, it's under the land. But that's a term that's in the book, and so I wanted to bring your attention to these two figures because I think they do a good job of illustrating how water that gets down below the surface is eventually going to migrate towards the stream, and the difference in speed. The Hortonian would be quick and the saturation would be slow. Okay. Another cross-section view of a stream and the difference between dry weather and wet weather, how the water table gets raised in wet weather and contributes to the stream flow. The saturation overland flow, I guess this is illustrating it maybe a little bit better than the other figure did because this is showing that it can re-emerge at the surface. You know, when the water table intercepts the surface, then this is now kind of like a spring where the water just seems to be coming out of the ground because it was raining previously uphill. So now the saturation overland flow is the base flow that is coming to the surface before it gets into the stream. Whereas in dry weather, it wouldn't actually, you wouldn't see it on the land. You'd only see that there's still some stream flow there. So I was initially wondering why I included both of those figures, but I think it's because this does a nice job of showing that the saturation overland flow was underground, but it came back up. We can break a hydrograph into a couple of pieces and ascribe different reasons for them. Sometimes this is kind of a strange hyetograph. Sometimes just for, I don't know, just to be cute, sometimes they'll put a hyetograph where the height of the bar obviously indicates how much rain there is, but then they'll do it downward, I guess, just to save vertical space or something. So, you know, it rained a little, it rained a lot, and then the rainfall slowed down again. And so what this figure is showing is that when the rainfall occurs, then it leads to a rising limb. And what you see first is the saturated overland flow. But then after the storm is finished, it still takes a while for that the falling limb to come back down. Like the rising limb is quicker than the falling limb. And the reason why it's so much slower is that water flows through the soil at a much lower speed than it can move over the surface of the land. And all of this flow, the base flow and the interflow, is related to water going through the soil pores at a low speed. Let's see. Excuse me? In this figure, why is it what? I don't know. That's a good question. Yeah, I'm not sure why it's just showing the saturation overland flow. Not sure. Okay. Before we start digging through differences in hydrograph shapes, let's take our customary break. It's 5:03, so we'll get started again at 5:08 and take a look at a couple more examples. Did everybody get my announcement about the computers? All right. So what we're going to do is look at several hydrographs and then try and predict how changes in geometry would affect the shape of the hydrograph. So things like the size of the contributing area, how steep the ground is, how rough the surface is, the length of a stream, and so on. So what this is showing, first of all, in the case of if you have a gentle slope compared to a steep slope, You're going to have a more flashy, rapid, high peak in the case of a steep slope because, remember, just think about it rained over a short period of time. This spread out hydrograph is saying that the water is concentrating to a single point of interest slowly, compared to the steep ground surface is having a all-at-once arrival of that rainfall pulse because it's traveling more quickly over the ground surface so that it's not diffusing over such a long time period. So does that first relationship make sense to everybody? Like why steeper ground is going to have a more concentrated arrival at the outlet? Okay, now consider the case of hydraulic roughness. What we're saying here is a smooth surface lends itself to an intense peak, whereas a rough surface is going to have a lower peak and a longer time of concentration. And by time of concentration, what I'm talking about is how long from time 0 to where we see the highest point. So who can explain why the rougher surface is going to cause this? It slows down the water. So why don't we just have that same shape but later than we see it? So why is it making the peak lower? Why isn't it just delaying but with the same shape?
Because the runoff from the lower surface is wetting all the surface and
Okay.
losing some of its energy, losing
Okay.
quantity of water.
That's a great way of looking at it, is that the water isn't just going over the top, right? It's wetting the surface. It's going sort of through the voids and everything. That's great. And remember the idea that if you have a channel and you just like, what if I have this water and it's like in a bucket and then I lift the bucket off? So the water is going to start traveling sideways in both directions. But really close to the bucket, it's moving quickly. But then as you get further away, because it's not like a big pile of water anymore, it's moving more slowly. And so it's diffusing. I guess the way to think about it is, I'm trying to think of a good analogy. Like if I opened a tear gas canister in this room and I set it in the corner, think about the tear gas would slowly be filling the entire room, even if there wasn't a fan. Like if we went and stood in the corner, we'd have fresh air for a few minutes, but eventually the tear gas would make its way just because of molecular diffusion. So what I'm saying, like what the point is that the longer it takes for the peak to arrive, it's going to be sort of spreading out the flow in both directions. Just like gas is diffused, the water is diffusing as it moves through the channel. And the word I used before, routing, is taking into account the travel times as the water goes, as water flows through a channel, that travel time, anytime there's a delay, it kind of smooths, it pushes down the peak because of the diffusion through the channel. All right, so storage. This is showing that there's intermediate storage that has to be satisfied, and it's going to be slowly releasing it. So it has the same effect of delaying the flow. Drainage density. High drainage density is talking about lots of little intermediate streams, so that the water doesn't have to travel very far over the surface before it gets into the network. Compared to a low drainage density, that means that there are very few streams, and so that most of the flow has to go over land before it gets into a stream. And that overland flow is much slower than channelized flow. For the length of the channel here, we're saying a longer length is going to reduce the peak because of that effect that we've already talked about, just the routing effect. Now, different things about the hydrograph shape. This is showing a front-loaded storm where most of the precipitation is at the beginning, compared to an end-loaded storm where even if it was the same amount of precipitation, just having it later in the day would mean that the peak is going to have a different shape. And so you don't always have the same hydrograph shape from a watershed. The hydrograph shape is in large part dictated by the geometry of the watershed, but it's also dictated by the timing of the rainfall. And that's what this figure makes the point of. And sometimes the storm is only just in a certain part of the watershed. In the case of Storm A, the water is falling far away from the outlet. It's falling in the furthest reaches, and so there's a long travel time before you see any peak. And that's why Storm A has this slow and gradual increase, is because it's a much longer arrival time compared to if the entire area is contributing all at once, including near the outlet, then the peak flows are going to arrive sooner than is illustrated for Storm A. And then even the direction of the storm. Like if you had clouds that are traveling from A towards B, where A is the outlet, if the storm originally is over the outlet and it's moving away from the outlet, from A towards B shows that the peak arrives sooner than if the storm is going from the furthest reaches towards outlet at A, then the peak is arriving later, because the storm is traveling kind of in the same direction as the water itself, and so the peak is higher, but it's later. So this is an important thing. Why is the peak higher? It's because more of the rain is arriving all at once, because the clouds are raining on top of the part of the stream that's currently carrying the water that used to be upstream, closer to B. And so this is kind of an unusual case where you actually could see delay but higher flows, because the rain is falling on top of where it's already wet. Okay. Earlier in the lecture I used this phrase rainfall excess. So it's the rain that isn't retained on the surface and it's not infiltrated into the soil. So rainfall excess is the leftover amount that's going to contribute to runoff. And so if we have a rainfall hydrograph here, and we subtract out the infiltration, and you'll note here that it has the declining potential rate of infiltration. So anything above that line is the leftover excess that is going to contribute to runoff. So infiltration is decreasing over time because the soil water pressure is decreasing as the wetting front gets lowered down, and then the suction pressure goes down. The language here of a hydrograph versus a hydrograph, we've already talked about that. But this is a really interesting diagram that shows how you go from a representation of the rain, and in the end what you want to know is how much water is going to be in the stream. And what this says is, the point that it's making in a series of consecutive figures is, first you start off with the rainfall, then you subtract out the infiltration amount to find the rainfall excess. You put the rainfall excess into a model that says what the hydrograph is going to be, and then you add the amount of water that's just from this storm to the water that was in the river even before the storm began. That's the base flow. And so that's the water that's a result of the groundwater that had been making it into the stream channel prior to precipitation. A unit hydrograph gives you a shape of what the runoff is going to look like for a single unit, whether it be an inch or a centimeter of rainfall excess. And there's a skill of, if you know what a watershed is going to do for 1 inch of rain, then you can predict with some accuracy what the hydrograph is going to look like for 2 inches of rain. You just scale the height of the watershed based on the unit hydrograph that you had to begin with. And so this is saying there's some typical shape. Now, assuming that the rain is falling equally over the entire watershed area. If it was only falling on a certain portion of the watershed area, then the unit hydrograph wouldn't necessarily predict of what you're going to see. But the principle here is once you know what it's going to do for the generalized storm that happens, then you can predict the shape for another storm. So the underlying assumptions here is that during the unit, the intensity is the same. It's a constant rainfall intensity, that it's evenly distributed over the entire watershed surface, and that the watershed itself isn't changing from over time. Like, it's not getting more urbanized. If you did your unit hydrograph analysis years and years ago, but now there's more parking lots and more houses, then you probably aren't going to have an accurate response these days. And this is where the rubber hits the road for the homework assignment, is if you know for one storm, for one unit, what the hydrograph looks like, then you can combine them together. Because the hydrographs that we've seen so far are like this. There's multiple steps, hour 1, hour 2, hour 3, and so on. So what we can do is we can take the typical response of a watershed to a unit of rainfall and layer it together. And so add hydrograph after hydrograph on top of each other and then come up with the resulting combined unit hydrograph. So multiple pulses of precipitation. So there's a formula that's in the book that says if you know what was the precipitation amount for the first hour and how much runoff you usually get during the first hour, that's what U1 is it's a factor related to the scaling ratio between precipitation and runoff. Then you can stagger different pulses of rainfall, and this it looks like a hydrograph, right? The shape of this looks very much like a hydrograph. And we're going to, with Excel, do the calculations that I hope will make this equation make more sense. These are at different times what rainfall has reached the outlet from a certain area. Now, look at P1 and the difference between the P's and the U's. And these are different areas. And so area 1 is closest to the outlet. And what we're going to call area 1 here, in this conceptual diagram here, is it is the area that can travel. If it rains over area 1 in 1 hour, then all of the water from area 1 will make it to the outlet. Area 2 is just like, if it rained on area 2, then it wouldn't be until the second hour that water makes it to the outlet. And so you think, like, if it rained for 1 hour over this entire area, then it's going to take a while for that flow to make it to the outlet. This is our unit hydrograph. This is saying that, like, in hour 6, for example, that's the 50 CFS that comes from this outer area, the furthest reaches of the watershed. But this is all just for if it rained during 1 increment of time. But what if, instead of just having it for 1 increment of time, what if we said during the first hour it rains everywhere, a ½ inch, then during the second hour, on top of that, on top of what happened before, it's going to rain 1 inch over the entire area. So you can see that there's 4 different periods here that there is precipitation. So this is P1, this is P2, P3, P4, and then this is U1, U2, U3, and so on. So this formula is showing, if you want to find out how much is at the outlet at any time, then you'd multiply the precipitation factor by the unit factor. And so that's what we're going to do using Excel. We're going to say, now assume that there's 0.3 inches per hour of abstractions. So this is the precipitation. We're first of all going to have to find out how much precipitation excess there is during each hour. And then we're going to apply the unit hydrograph to that. Okay, so start up Excel. We're going to create a table with this data. And I hope that this example will be pretty useful to you as you work on the homework assignment. Still working. All right. So with the blank workbook, we're going to have our unit hydrograph here. Okay. In the unit hydrograph, there's going to be time. We're going to go hours 0 through 6. And then in the example, this is basically the unit hydrograph that we're going to be typing in. What we know about this certain watershed is if there is 1 inch of rain, then this is going to be the pattern of the runoff. So runoff, Q, and this is going to be cubic feet per second per inch of rainfall excess. Let's do this. Okay. And so the data there is 0, 10, 100, 200, 150, 150. Now, we're going to combine that with our hydrograph. And so the hydrograph is basically rainfall characterization. And we're going to have the time in hours. We're going to have the precip amount in inches, the abstraction in inches, and then the rainfall excess in inches. Okay, so the table said that for the first hour, for example, there was 0.5 inches of rain. In the second hour, there was 1 inch of rain. In the third, 1.5. And then in the fourth hour, it was 0.5 inches of rain again. And the abstraction, according to the problem statement, is constant at 0.3 inches per hour. Okay, so we'll put in the 0.3 inches of rainfall, of abstraction for each of the 4 periods. So the rainfall excess is just going to be the difference between the precipitation and the abstraction. So equals precip minus abstraction. Okay. Okay, so now we've got the hydrograph table. And just for fun, I will put in some borders there. That was fun. All right. Any questions so far? Do you feel like you know what the unit hydrograph is? If it only rained 1 inch and it all happened in 1 hour, this is the flow rate we'd see coming out of our watershed. And I guess I should be more specific. It's not an inch of rain. This is for an inch of rainfall excess. So that means already taking into account satisfying all of the abstractions, satisfying interception, and so on. This is, after all that other stuff, or an inch of rainfall excess, this is the response that would be coming out of the watershed. Okay, so let's create now a runoff hydrograph. We're going to have time in hours going from the first hour all the way through the 10th. We're going to need 10 hours for this one. Okay, so going down here to 10 hours. All right. And then this is the rainfall excess during the period shown. Okay, so the period that this column is going to represent the first period, the first hour. And so let me, hour 1, hour 2, hour 3, hour 4. All right. So during hour 1, I'm going to multiply the unit hydrograph by 0.2 because there wasn't a full inch of rain. There was only 0.2 inches of rain. Okay, so equals 0.2, so I'm anchoring that reference, times the hydrograph amount for hour 1. I guess I could have started this with 0, but I didn't. So we get 2 CFS instead of 10 because it was just 2/10 of an inch. Okay, and I can drag that down through 6, and then after that it's just 0. There's no more flow rate afterwards. Okay, so that's the first pulse of rainfall making its way through the watershed. Okay, now hour 2, this is important. We need to stagger it. We need to delay by an hour. So I'm going to put in a 0 here because the hour 2 rainfall doesn't start arriving in hour 1. The first little bit of that second pulse of rainfall begins to arrive during hour 2. So it's going to be now equals the reference to 0.7. So I'm anchoring that cell reference and multiplying it by now the unit hydrograph and dragging this down through. Here. And then adding zeros afterwards. So do you see how it's staggered? The reason for the staggering is because the rain is coming an hour later. So is everybody with me so far? Any questions? I bet you can predict what to do for hour 3 and hour 4. Let's see what formula you got here for the first one. I'm just curious to see that. Okay, so click up there. Let's see. I don't know. Did it lock up or something? Let's see. It won't get you in there, huh? Try saving your file. I wonder if... oh, got it all. Oh, CSV. That's odd. No, say no. And save it, yeah, as an Excel workbook. Do you have any questions? Are you getting it okay? Typing in still? Okay. Can you say the first part of that again? Mm-hmm. Yep. Yeah.
Multiply this stuff by and get the flow.
Yep, exactly. Yep, if you know what it will do with 1 inch of rainfall excess, then you can project what it would do with 2. It's just going to be double, right? That's the idea, is that the rainfall excess is the multiplier that we apply to the hydrograph. So I'm going to put in 2 leading zeros for the 3rd hour and then 1.2 anchored times this hydrograph, dragging it down. That one needs to be a 0. And then finally the 4th hour will have 3 leading zeros before we have this amount times the unit hydrograph. All right, so then we have to combine it all together. And so we'll have a final one that's the total runoff in cubic feet per second. and add all of the 4 hours together. So it's arriving at different times. The contributing portion is arriving at the outlet at different times, but this is kind of, let me bring this figure back up again. Is where we are combining P amounts and U amounts at each time. And so you see how there's 3 different components here. I think this example that's shown here, there was only 3 rainfall pulses, P1, P2, P3. We have in our example here a little bit more complicated because there are 4 rainfall pulses. But you still have the idea that at any given 1 hour time increment, there's different contributing areas and different contributing precipitation amounts. So P1, P2, P3, then in the next one, it's applying to U5. Okay. So that's the idea that you need to apply for the problem 3 on the homework assignment. It's the same basic thing, but in traditional units, in SI units rather than traditional. All right. If you're still working on this, that's okay. Just remember that the video recording will have all of the steps that I did. So don't feel like you can't ever catch back up again. We're going to move on to some other things just because there's a few more things I want to help you out with on the homework. But this is there, and I hope you'll finish the example just to use as a good reference for when you have that assignment. Okay, unit hydrograph. Okay, so what if you don't have a unit hydrograph? There are ways to synthesize a unit hydrograph if you haven't actually measured one. A measured unit hydrograph means that you have to go out into a watershed with a stream gauge, and you have to have a precipitation gauge, and you need to have a storm that is 1 inch of rainfall excess occurring within 1 hour. So those are all pretty specific things in order to know what your unit hydrograph looks like. And so in the absence of physical measured data, what a synthetic unit hydrograph does is let's just use geographic parameters like the shape of the watershed, the length of the stream, the area of the watershed, and come up with a synthetic version, kind of like a fake unit hydrograph. And this is like fake cheese, it's not as good as the real thing, but it's kind of like an approximation, and it'll do in a pinch. It's better than nothing. I mean, that's arguable, but the main thing is that it's when the actual data is not available. Okay, so I have an example that shows a Snyder synthetic unit hydrograph approach. And the driving principle here is that you want to measure the lag time between the middle of the rainfall and the peak of the runoff. And once you've measured that T sub PR, then you can do a lot of projections based on that. Like it's an empirical procedure. They analyzed a lot of different watersheds where they did have a unit hydrograph available, and they looked at the area of the watershed, the length of the stream, and so on. So I have a handout for you that goes over some instructions. And we're going to just go through these steps one at a time and look at how you can synthesize a unit hydrograph from this. But it's not going to have the same visual appeal as an actual runoff hydrograph. From this one that we did, if we were to create a chart of this hydrograph, where the input X data is going to be time. So here's our time, and then we'll use for the Y data the total flow rate. It's a pretty nice looking hydrograph. It peaks up and then it comes back down again. Well, in the case of the synthetic unit hydrograph, it just assumes a triangular distribution. And it says there's going to be some peak flow. It's going to be longer for it to drain than the rising limb. And so let's go through. Here's the handout that shows you step by step. These same steps are summarized in the book, but I felt like the way they do it in the book makes some of the units a little bit unclear. So I've come up with this handout to try and clarify that procedure. All right, so you've got the handout there. Let's go through this example where the area is 5.42 square miles. The length of the main stream, L, is 4.45 miles. So you can write those numbers straight onto this example page here. L sub C, distance from the outlet to the watershed centroid. So what that means is, look at this shape. The watershed centroid is the center of area. So if we were just going to drop a pin in what looks like the center of area, it would probably be somewhere around here. And so if you measure the straight line distance from the outlet to the centroid, that's the L sub C parameter that they found was statistically relevant. And then these other regional parameters, C sub T and C sub P, are things that you'd have to look up out of tables of data. So we just take these as given. So we're going to go through and find the standard duration and then use the standard duration to find the synthetic unit hydrograph for a rainfall excess duration, meaning how long the storm lasts, is 30 minutes. Okay, so here's that handout, and let me give you a few minutes to do those calculations, and then I'll show you what I've got. We'll compare the numbers. So on the handout it says, what if you wanted it to be for a 1-hour storm? So if you want it to be, the T capital R is 1 hour, and I think what we're going to see is the peak would be 551 CFS per inch for the step 3 component, whereas if you change the timing of that down to half an hour, 0.5, as the desired duration, then it boosts it up to 570, because it's over a shorter time period. So the handout has a part A and a part B. On the slide, I guess I would need to edit the slide. We have to calculate the standard duration, certainly, but then to match the handout, this was the part B, but then there was also a part A for an hour. Sorry it didn't match initially. All right. Okay, so you know, like it's good to be aware of empirical procedures and empirical equations like this. The units don't make a lot of sense. Sometimes I get students asking, like, what is the 2581 for the C5 value and the 11.11? The units of that, just in case you're interested, are related to, let's see, I think I've got it here, are related to how many square feet are in a mile. And so, for example, there's an empirical factor of 4, and then there's 50 to 80 feet. If you square that, it's per square mile. And then if you convert, there's 12 inches per foot times 3,600 seconds per hour. What you end up with is 2581 cubic feet per second per square mile times an hour. And so if you multiply this number by your area in miles and you divide by the flow rate in CFS, then you'll get hours out of it. And where we were applying that conversion factor here, we were trying to find a time. And so, you know, we had A, which was an area in miles. We had Q sub PR, which was a cubic feet per second. And so the factor that makes the units into a time in hours, that C5 is going to have units that are shown here. So, you know, there is a section of the book that addresses this. It explains all of the steps and shows what the shape of the hydrograph should look like. Here in the solution, I illustrated that it's just going to be a triangular shape. And so if the peak flow rate is 570 CFS per inch of rainfall excess, then the meaning of the 14.09 that you calculate is that's when it finally goes back down to 0 again in the unit hydrograph. So these are better than nothing, but not likely to be exactly what you'd observe if you actually did a physical measurement of the runoff. Okay, one last thing we're going to talk about is called an S hydrograph. And if you have a unit hydrograph that has a certain duration, so like an example of that was this hydrograph that we were looking at here. This was caused by an inch of rain that fell within 1 hour. But you could also have a unit hydrograph. We could see what the response of the watershed is if that inch of rain came down during a 4-hour period. Or what if that inch of rain occurred during an 8-hour period. And so the S hydrograph method is a way of taking an existing hydrograph of a given duration. For example, if the rain occurred over a 2-hour period, and then you can convert it into the amount of rainfall that occurs during a 4-hour period. And so that's what here we're assigning the abbreviation T prime R. The idea is that the procedure that this is illustrating is that you take the hydrograph and you overlap many of them on top of each other. And that's what they're calling this S curve. And then you have to lag the S curve, meaning you displace it to the right by a certain amount of time. And what you do is you're displacing it by the duration of the rainfall that it was originally coming from, in this case 2 hours. And then you find the difference between the two S curves. So let me show you like what that all breaks down to, just as an illustration. Let's say that an inch of rainfall excess occurring over 2 hours gives you this hydrograph. Now this is a really big watershed. And so you'll see, although the rain is happening over 2 hours, that it doesn't actually, the peak doesn't travel to the outlet until 8 hours. And then it's draining for a long time after that. So we're saying for the same watershed, not changing any physical parameters of the watershed, it has the same area, it has the same slope, but what if just the rainfall patterns were a little bit different? What if instead of the rain sprinkling over 2 hours, what if it was over 4 hours? So before we do any sort of the procedure, I'm just asking you to think about like the logic of it. What do you think is going to be different if the rain happens over 4 hours instead of over 2? Do you think that the peak is going to be higher or lower? Okay, lower.
Same rainfall, same amount.
The same amount. So the same, good question, the same 1 inch, but you're spreading out the 1 inch over 4 hours instead of over 2. So what do you think is going to be different about that hydrograph? Peak's going to be lower, and what about the timing of it? Takes longer. So it's going to be later. The question is, how much? You know, what amounts? So we should expect that the peak is going to be later than 8 hours, and it's going to be lower than 389. Okay, so this is kind of like a tabular solution. The procedure here is create the S-curve, and the S-curve means just take this curve and overlap it many times by putting the numbers down on top of themselves. And so, for example, I wonder if I have the S-curve example here. It's easier than it looks. Okay, so here's the original data. Okay, 0, 69, 143, and so on. All right, so 0, 69, 143. Here's the original hydrograph. Okay, we make a lot of new ones. And you see, I'm starting the same hydrograph over. I just copy and paste 1 hour later. And then I paste it again an hour later. And over and over and over many times together. And then I add up all of the columns together, including the original. And so this is called the S-curve, is when finally it's going to reach some plateau. Like if I had more and more columns, then it would extend indefinitely. That's what this is showing, is you have many of these hydrographs added on top of each other, and so the flow rate just comes to some maximum plateau. That's what this column is the S-curve. Now the lagged S-curve is the same thing, so I take the combination and then I lag it by the duration here. I want it to be at 4, because that's what I'm trying to find, is the 4-hour hydrograph. So I paste the same one at 4 hours. Oops, what did I do wrong? I think I must have pasted the formula instead of the numbers. So I copy the numbers, Control C. Okay, I'm going to paste special, just the values here, rather than the equation. So I paste the values, and then you find the difference between the two. And so the lagged curve is this minus that minus that. Okay, so this one is going to be the original minus the lagged. And so you're always subtracting the two. Okay, so this is the lagged curve, but then look, it's not what we expected. We expected that if you spread out the same amount of rain over 4 hours instead of 2, the peak should be lower, right? But here, our original peak was 389. Now it's saying our peak is 717, so something's wrong. And the thing that's wrong is that this procedure naturally accidentally doubles the S-curve. And so you need to divide your result by T prime R divided by TR. So here, that means we're having to divide by 4 divided by 2. So we want to divide everything by 2 because that's the ratio of the new duration to the old duration. So here, in the final version of the hydrograph, I'm going to divide the lagged hydrograph by 2. Okay, so then drag that on down through. Okay, so here is our final resulting hydrograph, and this is the original. So let me paste it so that we can just compare what things were. So we can look and see if for the times that we expected it was doing the behavior that we'd expect. All right, so here in the original it was at 8 hours that we'd see 389, and that was 1 inch of rainfall during a 2-hour storm. Now the same 1 inch of rainfall during a 4-hour storm is only giving us a peak of 370. So it's lower. It's not a dramatically lower, but it is lower, and it's also later. That hits at hour 10 instead of hour 8. So both of those things that we predicted are true, but this is the new unit hydrograph during a 4-hour duration. Yeah?
So for the 2-hour duration, we had 0, 2, 4, 6, 8.
Yeah.
The 4 hours still have the same.
Good, that's right. Yeah, it's the same, this row still corresponds to time 0, this one is still time 2. So yeah, the x values are the same amount of time. It's kind of an abstract procedure, but hopefully seeing that illustration made some sense to you. That's all we're going to do talking about hydrographs. So just to reiterate the announcements from the beginning of the lecture, it's going to be a little bit different because we're not meeting next week. Instead, what you're going to do is you're going to take this homework, and if you'd like to get an early start on it, you certainly can, maybe while some of these things are fresh in your mind. But if you need my help, then I'll be happy to see you during my office hours. But the homework itself isn't due until the 8th. What's the more immediate thing is that magically at 4 p.m. on Wednesday the 1st, that exam is going to show up. I'm going to be in Dubai, and so Dubai I think is 8 hours ahead, right? Is it 7 to Saudi from here?
7 hours.
Right now? Yeah, so Dubai is 1 hour ahead of Saudi, I think.
Yeah.
So 8. So it's going to be midnight. The point is, when your exam starts, it's going to be midnight. I'm not going to stay up and wait until you've submitted it at 10. That'll be in the morning for me, 6 a.m. So I'm not going to be able to help you interpret any problem statements. Part of the exam is applying your experience till now and your understanding of the material to make reasonable assumptions about what I mean on a certain question. But I hope that it goes well, and if it's just an absolute train wreck, then we'll pick up the pieces when I get back. But I think it should be fine. It's the same method that we've been using for the homeworks. They're available online, and you submit it online. So I think we've had some practice till now. Any questions before we wrap up? All right. So I'll see you then in 2 weeks from today. I'll bring something. I'll try and